The Embraer 170 is equipped with two GE CF34-8E turbofan engines. Each engine is housed in an aerodynamic nacelle suspended by a pylon installed under the wing. The engine produces maximum power from 13,800 pounds up to 14,200 pounds on the reserve mode, RSV, at ISA condition. The engine is a high-bypass, two-spool, axial-flow turbofan engine. It can be divided into the following modules: the cold section, the accessory gearbox, the combustion liner and Stage 1 nozzle assembly, the high-pressure turbine, and the low-pressure turbine. The engine basic characteristics are a single-stage, low-pressure fan that is driven by a four-stage, low-pressure turbine. This spool represents the N1 speed indication on the cockpit. A 10-stage axial flow compressor with variable geometry inlet guide vanes and stator stages driven by a two-stage high-pressure turbine. This spool represents the N2 speed indication on the ICAS. A dual-channel full-authority digital electronic control, FADEC, provides flexible engine operation, reduced pilot workload, and the highest level of reliability, safety, and maintainability. The accessory gearbox provides mounting pads for the electric alternator, IDG, and the hydraulic pump. 5 thermocouples mounted in the inlet stream of the low-pressure turbine sense the gas temperature and send their signals to the FADEC. The signals are used for ITT indication, hot start logic, and flame-out detection. Engine fuel flow is measured within the fuel control unit that also sends a signal to the FADEC and to the ICAS for indication. The engine fuel system has two subsystems, a fuel control system and a fuel distribution system, which provides the engine with scheduled fuel for combustion. The engine fuel control system is composed of a two-channel full-authority digital electronic control, FADEC, a fuel metering unit, FMU, a permanent magnet alternator, PMA, engine sensors, variable geometry, VG, actuators, and an operability bleed valve, OBV. The components of the fuel distribution system include the fuel pump, fuel filter, fuel manifold, and 18 fuel injectors. Fuel from the aircraft fuel tanks enters the engine at the engine fuel pump inlet. From the fuel boost pump, the fuel splits inside the pump housing and is either directed to the FMU or is returned to the aircraft as motive flow for the tank ejectors. The fuel that is discharged from the fuel pump is directed to the fuel oil heat exchanger, which is used to cool the engine lubricating oil and also to heat the fuel for icing protection. From the heat exchanger, the fuel enters the fuel filter, which is contained in the FMU. From there, the fuel is returned back to the fuel pump to increase the fuel pressure before it enters the FMU. The FMU meters the fuel by means of FADEC inputs and sends this fuel by way of the fuel manifold to the 18 fuel injectors mounted in the combustor frame. The fuel control system is managed by a two-channel full-authority digital electronic control, FADEC. The FADEC controls the engine fuel requirements in response to thrust command inputs from the aircraft. The FADEC software provides thrust management based on aircraft and air data inputs. These inputs are used to calculate appropriate reference N1 for any given thrust lever position. Some of the N1 references are modified by discrete inputs like Automatic Takeoff Thrust Control System, ATTCS, Thrust Reverser Position, Weight on Wheels, and Bleed discrete inputs. In addition to setting the correct N1 for a given TLA position, the FADEC schedules limit fuel to protect the engine speeds, temperature, and compressor discharge pressure (CDP) limits. The engine fuel indicating system is monitored by engine-mounted sensors that provide their information to the ICAS. The indicating system consists of a fuel filter bypass switch, a fuel low-pressure switch, and a fuel flow measuring device. Engine fuel system operation begins with information supplied by the FADEC and provides steady-state and transient regulation of thrust while protecting engine limits. One FADEC channel operates as the in-control FADEC channel, providing electronic control outputs. The other FADEC channel operates as the standby FADEC, processing all inputs but with all electronic control outputs disabled during normal engine operation. During operation with two capable FADEC channels, in-control software logic will cause the FADEC channels to alternate control on each successive engine start. Main FADEC power is supplied by the PMA during engine operation, with a 28-volt DC airframe input for starting and backup. Thrust control of the engine is provided by the FADEC, with thrust management based on aircraft and air data inputs. The main thrust setting inputs are the thrust lever angle, TLA, and the air data from the engine and airframe sensors. These inputs are used to calculate appropriate reference N1 for any given thrust lever position. During normal engine operation, the FADEC will control to a physical N2 or a P3 reference at idle thrust lever settings, and to a physical N1 reference at any power above idle up to maximum power. The purpose of the engine oil system is to provide lubrication and cooling to the turbine engine main shaft bearings and the accessory gearbox bearings. The engine lubrication system contains the following main components: an oil reservoir, which is an integral part of the accessory gearbox, the lube and scavenge pump, the oil filtration module, which includes a filter bypass valve, and the fuel oil heat exchanger, which cools the oil and heats the fuel. The engine oil system can be monitored on the ICAS and MFD status page. The ICAS indicates the engine oil pressure and the oil temperature. The engine oil pressure readout is displayed in pounds per square inch for each engine. Indication is green in normal operation, amber when operating in the cautionary range, and red when operating limits are exceeded. The engine oil temperature readout is in degrees Celsius for each engine. Indication is green in normal operation and amber when operating in the cautionary range. Engine oil level status is displayed on the MFD status page in quarts. Each engine has its own scale with pointer and a numerical display. The left scale corresponds to engine 1, and the right scale is for engine 2. The scale is divided into two segments. The bottom segment is the amber region, and an upper segment, which is displayed in white, is the normal region.
The ignition system provides an electrical spark for fuel combustion during on-ground engine starts, in-flight starts, and in-flight auto relights. The FADEC energizes one igniter for on-ground engine starts and both igniters for in-flight engine starts. When the ignition selector knob is placed in the override position, both igniters on each engine are energized. Igniters 1B and 2B are connected to SPDA2. In case of SPDA2 failure, setting the selector knob to override energizes at least the igniter A.
Engine ignition is controlled by the FADEC and integrated aircraft systems that automatically initiate ignition in response to engine core speed developed by the starter air system. Only one igniter is energized for ground starts so that latent faults can be detected. Two igniters are energized for air starts, flameouts, loss of ARINC buses, a missed light-off, or if continuous ignition is requested by the pilot. Selection of the ignition system can be performed manually from the engine control panel by selecting the ignition selector knob to the off, auto, or override position. When ignition is selected to the auto position, the FADEC automatically controls the ignition system. Depending on engine requirements, when ignition is selected to the override position, the FADEC continuously activates both exciters when the engine is running. The FADEC will deactivate the ignition system under the following conditions: upon engine shutdown, or when the pilot sets the ignition selector knob to off during dry motoring on ground. In flight, the FADEC disregards the off position. The FADEC activates both igniters whenever a flameout is detected in flight or on ground. When this occurs, a fail indication is displayed in the center of the N1 dial. A windmill indication is displayed beside the respective N2, indicating that the engine auto relight attempt is in progress. The ignition remains on for 5 seconds after the flameout detection has been cleared. If the engine relight does not occur within 30 seconds when the N2 rotation is below idle, moving the start-stop selector knob to the stop position will terminate the auto relight.
The engine starting system is designed to provide sufficient rotor speed to initiate combustion light-off and to obtain self-sustaining engine propulsion. The starting system includes an air turbine starter, ATS, and a starter control valve, SCV. The pneumatic system provides bleed air to the ATS to rotate the engine rotor and start the engine. Engine starting is a combined aircraft and FADEC operation. The FADEC controls fuel flow, the starter command, and the ignition command, while the aircraft controls the starter control valve and the engine-driven pump, EDP, of the hydraulic system, and also switches power to the ignition exciters as commanded by the FADEC. The aircraft also manages the bleed system interface during starts. By selecting the Start/Stop selector knob on the engine control panel momentarily to the start position, pressurized air is directed to the air turbine starter, which rotates the engine rotor via the accessory gearbox. The FADEC automatically commands the ignition and fuel flow on. The FADEC schedules the fuel flow to accelerate the engine to idle, de-energizes the starter control valve at approximately 50% N2, and turns the ignition off. Note that the isolation valve is automatically controlled only if the X bleed switch is selected in the pushed-in auto position. For windmill start, the engine rotors are rotated by the aircraft forward airspeed, providing windmill rotation. The start is commanded through the Start/Stop selector knob, and the FADEC then automatically commands ignition and fuel. Note: The hydraulic engine-driven pump is unloaded by energizing the engine-driven pump solenoid during engine windmill starts in order to reduce drag on the core rotor. An assisted start sequence is carried out as follows. The ignition switch is placed in auto position. The bleed air system is then configured so that air at the starter control valve is available. The start-stop selector knob is momentarily selected to start so that the MAU senses the start switch closure and sends the start switch signal to the FADEC. The starter control valve opens. The FADEC commands the ignition on at approximately 7% N2, and the fuel metering valve to open at approximately 20% N2. The FADEC will schedule the fuel flow to accelerate the engine to idle and will de-energize the starter control valve at approximately 50% N2. An in-flight assisted start is identical to an on-ground start, but the FADEC will open the metering valve if N2 has not reached 20% after 15 seconds. A windmill start is performed according to the following sequence. The ignition switch is set to auto. The start-stop selector knob is momentarily set to start. The switch position is sensed by the MAU, which sends the start switch signal to the FADEC. Since no pneumatic pressure is available, the starter control valve does not open. The FADEC recognizes that the starter control valve remains closed after the open demand and automatically commands ignition at 7% N2 and fuel flow at 7.2% N2. Or after 15 seconds if 7.2% N2 is not yet reached. The FADEC will schedule fuel flow to accelerate the engine and turn off ignition as idle speed is reached. Note, the FADEC has no protection for hot starts, hung starts, or failure to light off for in-flight engine starts. If no light off is detected within 30 seconds after fuel flow is started, the start should be manually aborted.
The FADEC start protection logic provides automatic hot, hung, and no light-off start protection with the aircraft weight on wheels. Hot and hung start protection is inhibited in the air so that the FADEC cannot prevent an in-flight start. The hot start protection will terminate the start when internal turbine temperature rises above 815 degrees Celsius during a ground start, by closing the fuel metering valve and shutting off ignition. The FADEC will not de-energize the starter driver in this case to allow immediate engine cooling by motoring. To terminate motoring, the start-stop selector knob has to be moved to stop. In the event of an engine flameout, the FADEC monitors the N2, automatically turns on both igniters, and schedules the relight fuel flow. In addition, a windmill icon is displayed next to the respective engine N2 and represents an auto relight actuation during the engine auto relight attempts. If the engine relight does not occur within 30 seconds, or N2 falls below 7.2%, the automatic relight can be considered unsuccessful and should be manually terminated by moving the start-stop selector knob to the stop position. During ground operations, auto relight attempts are terminated and fuel is shut off if the engine RPM falls below 52% N2. The exhaust system of the engine discharges the primary and bypass air from the propulsion system. The exhaust system includes the nozzle and the thrust reverser system. Primary air is the air which enters the engine near the fan blade platform, continues through the high-pressure compressor, the combustor, the high and low-pressure turbines, and then is accelerated and exhausted to atmosphere through the primary nozzle. The inner wall of the primary nozzle and the outer wall of the center body form the primary nozzle flow path. The thrust reverser assembly is located directly aft of and is clamped to the aft fan case. It forms a duct for fan exhaust air when the left and right assemblies are latched in place. Each thrust reverser half consists of a fixed structure that supports the transcowl, houses the cascades, and contains the thrust reverser actuation system. In the forward thrust configuration, the transcowl is in the forward stowed position covering the cascades. In the reverse thrust configuration, the transcowl is in the aft deployed position, blocking the fan duct and exposing the cascades. The assemblies have a translating cowl that moves aft when commanded by the thrust lever, resulting in a redirection of the fan airstream during reverse thrust operation. Each thrust reverser half is operated by two hydraulic actuators pressurized by the aircraft hydraulic system. The actuators extend when reverse is selected and drive the transcowl aft along tracks on the upper and lower beams of the thrust reverser fixed structure. Appropriate interlocks and position sensors, which indicate the position of the transcowl to the flight crew, are incorporated in the system. The thrust reverser is controlled from the cockpit through a thrust reverser control integrated into the thrust control quadrant. This allows the thrust reverser to be deployed or stowed by hydraulic actuators mounted in the thrust reverser. The FADEC receives various inputs such as weight on wheels, wheel speed, and thrust lever angle from the aircraft systems, and activates the system logic when all signals are correct for reverse thrust. Once the thrust lever is retarded into the reverse range of the quadrant, the cowl lock and direction control unit are energized, which enables the thrust reverser to be deployed. The thrust reverse deployment occurs only if the airplane is on ground and the respective engine is running. Moving the thrust lever to idle enables the lifting of the thrust reverse trigger. Moving the thrust lever to the reverse position commands the thrust reverse deployment. During normal operation, the FADEC will limit the thrust to idle until the thrust reversers for both engines are fully deployed, thereby minimizing the possibility of uncommanded asymmetric thrust. If the engine is inoperative, the thrust reverse trigger is not released, so the respective thrust lever cannot be moved to reverse position. However, full reverse thrust remains available on the operative engine. Note: the thrust reverser is not designed to operate in flight, and uncommanded thrust reverser deployment limits engine thrust to flight idle. The engine thrust control is provided by the thrust management system within the FADEC and controls the engine in response to thrust command inputs from the aircraft. The aircraft provides 28-volt DC from the essential bus to each FADEC channel for system power when the engine is not running, or when performing a FADEC-controlled engine start with an engine speed below 50% N2. 28-volt DC from the essential bus is supplied for T2 sensor anti-icing and 115-volt 400 Hz power to each ignition exciter. Selection between the aircraft 28-volt DC from the essential bus and the PMA power is performed automatically by the FADEC when the engine speed is greater than 50% N2. The engine monitoring function is also performed by the FADEC by monitoring inputs from various sources and by performing tests for failures and over-limit conditions. The FADEC supplies ARINC 429 outputs of engine parameters and status to other aircraft avionics, and supplies information to aid in detection, reporting, and storing of faults, engine dispatch level and exceedance information, and data for trend data records. The FADEC will perform diagnostics on its input data to determine if any failures exist. If a failure exists, and if the failure is one that the pilot should be aware of, a message or indication will be displayed. The Thrust Control Quadrant, TCQ, is located on the aircraft cockpit center console and combines two lever assemblies, one for each engine, which may be operated independently, in unison, or in auto throttle mode. The full travel of the thrust levers is 85 degrees, divided into 5 settings, which provide the RVDT's output signal corresponding to max reverse at 0.5 degrees thrust lever angle, minimum reverse at 12 degrees thrust lever angle, idle at 22 degrees thrust lever angle, takeoff go-around at 75 degrees thrust lever angle, and max power at 85 degrees thrust lever angle. These 5 settings are also identified and illuminated on both sides of the thrust control quadrant. The thrust control quadrant case is provided with 2 soft détentes, grooves, one at takeoff go-around, 75.0, and the other at minimum reverse, 12.0. The max reverse position is achieved by pulling the thrust lever against a spring. Positive adjustable stops are provided at the max and max reverse positions to limit the movement of the thrust levers. Thrust levers are capable of unrestricted forward movement from idle to max power. 2 electrical idle stop solenoids, one for each thrust lever, are installed on the thrust control quadrant at the 22.0 degree TLA position. These solenoids provide protection against thrust lever command below idle in flight. Power to these solenoids is provided by the SPDA and allows selection of reverser thrust immediately after touchdown and during ground operations. Position indication is provided by 2 microswitches, one for each solenoid, which sense the idle lock shafts and trigger messages on the ICAS whenever the solenoids become unlocked during flight or locked on ground. The toga switches are mounted on each thrust lever to enable the pilot to manually generate a takeoff go-around signal. They are momentarily push-button, single-pole, single-throw. The AT disc switches on each thrust lever enable the pilot to manually switch off the auto throttle system. The auto throttle servo drive with associated control electronics is provided for each lever. The servo drive features a motor and gearhead combination to provide required force to operate each lever. The Automatic Takeoff Thrust Control System, ATTCS, controlled by the FADEC, automatically provides engine thrust reserve in the event of an engine failure during takeoff, go-around phase, or wind shear warning detection. The Takeoff Dataset menu page on the MCDU provides Automatic Takeoff Thrust Control System mode setting. The Automatic Takeoff Thrust Control System status, on, off, may be selected via the MCDU on the Takeoff Data Set page. However, if no selection is made before takeoff, the system assumes status on by default. The ATTCS is armed when either thrust lever is at takeoff go-around position during takeoff, when automatic takeoff thrust control system is selected on the takeoff data set page, or during a go-around. The automatic takeoff thrust control system is activated manually whenever the system is armed and either thrust lever angle is advanced above takeoff go-around position. If automatic takeoff thrust control system is activated, the green ATTCS indication disappears, and the cyan thrust mode will be displayed with an additional RSV indication. Flexible takeoff is a reduced takeoff thrust setting based on assumed temperature. The FATEC determines flexible takeoff rates for any of the three possible takeoff modes, reducing the takeoff thrust based on assumed temperatures set on the takeoff data set page. The indication Flex Takeoff 1, Flex Takeoff 2, or Flex Takeoff 3 will be displayed on the ICUS for the respective flexible takeoff thrust. The flex takeoff reduction is limited to climb thrust. For CF34-8E5A1 engine, flex reduction is limited to climb 1 when takeoff 1 or takeoff 2 is selected, and limited to climb 2 when takeoff 3 is selected. For CF34-8E5 engine, flex reduction is limited to climb 1 when takeoff 1 is selected, and limited to climb 2 when takeoff 2 is selected. For CF34-8E2 engine, flex reduction is limited to climb 1. Automatic takeoff thrust control system function does not interfere with the flex takeoff reduction. The thrust management system is configured in a dual redundant architecture, designed for increased system availability. Only one channel of the thrust management system, as well as only a single thrust rating selection, one electronic thrust trim system, and one auto throttle are operating at any given time. The pilot can select the priority auto throttle channel, as well as thrust rating selection and electronic thrust trim system channels via the MCDU. Thrust rating selection. The thrust rating selection determines the appropriate thrust rating upper limit based on the phase of flight when in auto mode or based on pilot selection when in manual mode. The selected thrust rating in either auto, thrust rating selection determined, or manual, pilot selected, rating mode is displayed on the ICUS display for pilot reference rating bug, and is used by the auto throttle when engaged so as not to exceed the determined thrust rating upper limit. The auto rating or one of the manual ratings is selected on the MCDU on the thrust rating select page. The selected thrust rating mode, either auto, go-around, continuous, climb, or cruise, is indicated in green on the MCDU. Takeoff Dataset. The Takeoff Dataset, TDS, works within the thrust rating selection system to allow the pilot to change the default takeoff thrust rating in order to accommodate for the different takeoff conditions and prolong engine life while making efficient use of fuel. The three possible takeoff datasets are Takeoff 1, Takeoff 2, and Takeoff 3. These selections are made on the MCDU on the Takeoff Dataset menu page. The emergency shutdown subsystem provides a way of controlling the flow of fluids and air to and from the engine during emergency procedures. In an emergency situation, the pilot can stop the engine immediately by pulling the fire handle. This action stops the fuel flow to the engine and also stops the flow of the hydraulic fluids and pneumatic air from the engine to the aircraft systems. Pulling the related fire handle will stop the engine in an emergency situation. The fuel shutoff valve will close the valve, which stops the fuel supply to the engine. The hydraulic system shutoff will also close, isolating the engine side of the hydraulic system from the airframe hydraulic system. The handle also generates a signal which is sent via the MAU to the air management system, which closes the high-pressure shutoff valve and the engine bleed valve. This isolates the engine air system from the airframe systems. In the following interaction, you can select and close the valves. Carefully observe the effect the valve closing has on the system. The N1 is a primary engine instrument and is displayed to the crew as a dial, pointer, and digital readout for each engine. The N1 digital readout is a numerical display of the fan rotor speed, displayed as a percentage of total RPM for each engine. The N1 digital readout is displayed whenever N1 information is valid. The N1 dial provides a graphical representation of the current N1. The N1 for each engine is indicated by a rotating analog pointer. The dials display pie-shaped shading in the area between the 0% position of the scale to the current pointer position. There are two arc segments that make up the N1 dial. Segment 1, 0% to N1 red line, represents the normal range of N1. And segment 2, red line and all positions higher, is the red range of N1. In the event of a loss of N1 signal, N1 pointer is removed from the display. The red line is the exceedance threshold and represents the maximum allowable N1 value. The N1 reference arc displays the difference between the actual N1 value and the requested N1 value applied by the thrust lever position. The N1 wing anti-ice WAI bug is displayed on the outside of the N1 dial. The N1 wing anti-ice bug indicates the minimum N1 value when the wing anti-ice is on and the aircraft is on the final approach phase. The thrust rating annunciation is displayed as text in the center above the N1 dials. Selected thrust rating is provided by the thrust rating selector, TRS, and is based on phase of flight. A flex takeoff is used to reduce the engine thrust, to account for favorable takeoff conditions. An N1 rating bug is displayed at the corresponding N1 value on the dial. Takeoff thrust ratings are selected via the MCDU on the Takeoff Dataset menu page. The flex temperature limits thrust to a value less than the active takeoff rating if the flex takeoff option is selected on and a flex temperature is set to a value greater than the takeoff temperature, pilot inputs. Flex temperature is displayed between the N1 dials below the ATTCS status annunciation. Flex temperature is selected via the MCDU on the Takeoff Dataset menu page. The max thrust is the maximum allowable N1 value that can be selected moving thrust levers to the max position. Max thrust is displayed for each engine as a tick mark on the N1 dial. The maximum N1 value will always be lower than the N1 red line. When ATTCS is enabled or armed, it is enunciated with the label ATTCS above the N1 dials. If ATTCS is active, in case of an engine failure, the ATTCS annunciation is removed from the display and TO1 RSV, TO2 RSV, TO3 RSV, or GA RSV are shown. When an engine is shut down by crew action, the engine shutdown annunciation off is displayed in the center of the N1 dial for the affected engine. When an engine flames out or is shut down without crew action, the engine shutdown annunciation fail is displayed in the center of the N1 dial for the affected engine and a caution CAS message is displayed. The thrust reverser annunciations are displayed under the N1 dials whenever the thrust reverser is not stowed. This is shown with the annunciation REV. An amber REV annunciation if the thrust reverser is transitioning from one state to another, stowed to or from deployed. The annunciation is displayed in red inverse video in case of an inadvertent deployment in the air, and a CAS message will be displayed. The ITT is a primary engine instrument and is displayed to the crew as a dial, pointer, and digital readout for each engine. The ITT readout is a numerical display of the inter-turbine temperature for each engine, displayed in degrees Celsius. The ITT dial provides a graphical representation of the current inter-turbine temperature. ITT for each engine is indicated by a rotating analog pointer. The dials display pie-shaped shading in the area between the beginning of the scale to the current pointer position. The ITT red line represents the maximum ITT for the certified thrust rating modes. The lengths of the arc segments on the ITT dial and the location of the red line tick mark vary depending on the red line data provided by the FADEC. The ITT amber line is the limit that corresponds to the maximum continuous ITT limit. The ITT amber line is displayed on the ICUS only in flight after the end of the takeoff phase. The engine fire annunciation indicates detection of an engine fire condition for the engine. The igniter annunciations indicate the various states of the igniters for each engine. The label A and or B or off annunciations are displayed under the IGN label. The possible annunciations are: IGN A indicates igniter A has been commanded on. IGN B indicates igniter B has been commanded on. IGN A B indicates igniters A and B have been commanded on. IGN off indicates igniter locked off. The N2 is displayed as a digital readout for both engines. If the N2 value is invalid or outside of the displayable range, the N2 digital readout is replaced with 3 dashes. For each engine, the WML annunciation is displayed when conditions of an engine flameout is detected and the engine has not been returned to its running condition. The fuel display consists of digital readouts for left and right fuel flow, left and right fuel tank quantities, and total fuel quantity. The units for fuel are pounds or kilograms as determined by aircraft configuration. This is not crew selectable. The fuel flow in kilograms or pounds per hour is displayed for both engines as digital readouts directly under the N2 display. If the fuel flow data is invalid or outside of the displayable range, the readout is replaced with 3 dashes.
The Integrated Engine Vibration Monitoring System indication on the ICAS consists of one indicator for each engine and is divided into an LP and an HP scale. The LP indicator represents the N1 rotor and the HP indicator represents N2 rotor. The indication will be shown in green from 0 to 3.9 and in amber from 4 to 5. In case the integrated engine vibration monitoring values are higher than 5, the maintenance computer and flight data recorder will be able to continue recording vibration levels up to 10 units. Note: transient LP or HP high vibration indication without any other abnormal engine parameter indication may be considered normal according to the engine manufacturer.